Okay, finally, I can start. Seems like forever. Hi everyone, thank you for coming along. This is the Friday 3 p.m. version of Trying to Keep You Awake, starring CosmosDB. I'll do my best to do that, keep you entertained along the way. I know it's sort of getting long in the tooth. It's been a big few days, so hopefully not only will it be entertaining, maybe a little informative as well. So what I'm hoping you'll get out of this is initially there's going to be a bit of a story and an explanation around some of the key concepts of CosmosDB. That's kind of going to be a bit of a knowledge leveling, if you will, just to make sure we're all on the same page and we understand some of the core concepts. And that'll probably be the first half. The second half will go into some important design considerations on CosmosDB itself, but also onto the on the client side as well, which is just as important. And this is all based on real-world stuff that I've done in production and before production. So I've experienced all these pain points. There will additionally be a swear word in there, so you may want to cover your ears, but you won't see it coming anyway. Well, cover your eyes. There's only one swear word, it's only small. My name is Paul Gavich. I'm currently a principal consultant at Replication. Been there for about 2.5 years now. I've authored a few books on this group called an ASP Insider group, which is fairly close to the ASP.NET team. If you count New Zealand, I'd be an international speaker, and I'm going to count it because it sounds better. And mostly into cloud and solution architecture as of late. But just to set the context, we'll talk a little bit about before cloud. Not so much before cloud, it could even be now as well. Traditionally, when dealing with big data stores and high availability data stores, big performance, we're talking about big memory, lots of CPU, lots of disk. We had to manage and set up all that ourselves. There was lots of backups we had to worry about. Where do we put the backups? How often do we do them? Log shipping and transaction replication. We often had to set that up, make sure there was enough network bandwidth in between those locations and set up those locations perhaps in different parts of the world. There was lots of things we had to manage, particularly insofar as clusters and multiple clusters, geo-redundant clusters. It was a lot of work for usually a series of full-time employees. So that was just a dedicated job to do that. And there's a huge upkeep in that. Fast forward to the cloud, and what a lot of the cloud providers would like to do is kind of abstract all that hard work involved with getting all that geo-redundancy, the backups, the transaction replication, and just allow you to work with the data store mechanism so that you only have to worry about the data operations, and all that really complex hard stuff is taken away for you. Obviously at a cost though. But like with anything, it's sold as a bit of magic, but it does come at a cost. You need to take into account a few design considerations so that you get the most out of it. Otherwise it's just going to seem like it's not working for you. And that's what we're going to talk about here, specifically with CosmosDB. But as to its history, it initially started out in around 2010. It was an internally developed system by Microsoft to do just that, in that give their developers the power to just worry about data operations and not have to worry about the servers underneath. In around 2014, it was brought to the public as something called DocumentDB. It's primarily just a JSON NoSQL store, if you will. And then not long after that, it was rebranded as CosmosDB with a whole bunch of extra features and vision around it. It is cloud native in that it doesn't care about being on premises ever. It's just designed with the cloud in mind, and so it can reduce the amount of constraints and only worry about a specific use case there insofar as it's only going to be developed for the cloud. It doesn't have to worry about this on-premises rubbish. And another big caveat before we go too far into it, it can be expensive. Depending on how it's set up and how much throughput you need. And I guess, if you're not taking into account some of the considerations with Cosmos, you just kind of want to dial it up expecting huge amounts of performance, maybe you'll get it, but it'll generally come at a bit of a cost, so it's something to be aware of. It's probably one of the main downsides to it currently. However, don't take my word for what Cosmos is. This is actually an excerpt from Microsoft's site, and it's traditionally bad presenter etiquette to actually read this out, but I'm going to do it anyway just for dramatic effect. As CosmosDB was built from the ground up with global distribution and horizontal scale at its core, it offers turnkey global distribution with multi-master support across any number of Azure regions by transparently scaling and replicating your data wherever your users are. Elastically scale through throughput and storage worldwide, and only pay for what you need. Azure CosmosDB provides native support for NoSQL choices, offers multiple well-defined consistency models, guarantees single-digit millisecond latencies at the 99th percentile, and guarantees high availability with multi-homing capabilities and low latencies anywhere in the world, all backed by industry's leading comprehensive service level agreements. Just take a moment to whisk that in and let that sink, that intellectual verbiage sink a bit. So that should clearly explain it, right? And usually when most sort of people in the IT industry get told something like that, again, it takes a little bit to sink in, and they usually come to roughly the same conclusion. There's a swear word just for a spoiler. But it's not that. It is all those things. It's not the most easiest to digest explanation. And underlying those things is a lot of key concepts. First off, when you provision Cosmos, you provision a CosmosDB account. You'll provision one or more databases. Within those databases will be one or more collections, and those collections will contain documents. Roughly the same as kind of a collection might be looked at as a SQL table, and the documents in there obviously as records in a database, something similar to that. One of the main key concepts is partitioning. It's the key to how Cosmos scales, so you really need to accept and understand this and kind of work with it with Cosmos, otherwise it's not going to work how you expect. And with a partition comes a partition key. If you have a static partition key, for example, Cosmos is not really going to work that well for you. You really need to embrace this concept of partitions. Cosmos will scale out, whereas something like SQL Server just wants to scale up, which is the big CPU, more memory. And how Cosmos works in terms of defining its throughput is this thing called request units. And if you're familiar with Azure SQL and its D2Us, it's roughly similar in that it's kind of an aggregate of CPU, memory, I/O, throughput, those kinds of things. You provision how many request units you want, request units per second. Starts off a minimum of 400. It can go up to 1 million or millions. You can go quite high actually, and in theory, you can scale that out as much as you want, up to a point at all costs, and I'll show you how much that may cost later on. You can provision that per collection or across the entire database. You can have a database with multiple collections, and you can provision your request units across those and shared across these multiple collections. There's optionally a reserve model where you can say, I want to buy, 10,000 RUs for 6 months or a year, and you'll get a reduced pricing from that. If you purchase, let's say, 10,000 RUs and you exceed that, Cosmos will refuse the request and you'll get this status code of 429 saying request rate throttled, and you'll need to retry the request. Now I've come up with the analogy of how to explain partitioning in particular as commuters going to or catching a train. So if you think that the data operation is actually the commuters coming into the train station, the turnstiles there are what is in effect the client proxy. So say for SQL, you're going through a SQL client. With Cosmos, you've got a document client. And of course, the train is the data store mechanism. And for the traditional relational store, it's nothing particularly spectacular, although the animation itself is spectacular. It took me ages to do. And if you have a lot of data with a traditional relational store, you'll just get a bigger server to cope with the extra load. It's pretty simple stuff. With Cosmos, it's a little bit different. So you've got some data coming in, and Cosmos itself just farms it out to different partitions, ideally. We'll look at that in a bit more detail later on. So as the data's coming in, it's just farming it out and spreading in the load across different partitions. Now, if you've got a lot of data, typically with Cosmos, again, it'll farm it out to different partitions, but it wants it in a parallelized format. So if you can parallelize your data as much as possible, it'll deal with that even better. You'll get really high throughput, as evidenced by, again, this spectacular animation. That's the pinnacle of my career, actually. I could just drop off the face of the earth now, and as long as I've given that animation to you guys, I'm all good to go. However, replication. Cosmos offers, we talked about SLAs and geographic redundancy and replication previously in that verbiage from Microsoft, but it does offer really, really good replication capability. So you can elect to replicate your data in unlimited read replicas around the world. So you've got somewhere where you might be writing data to, so that's called your write master, and you can elect to replicate anywhere across the world. And we'll do that a bit later on. It's really, really simple. What's coming up recently though, and sorry, with the read replicas, when there's a failover in your write master, you can elect or have a priority order about where your next write master becomes available out of your read replicas. Now obviously the more you replicate, the more hardware and resources are being used, so you're going to pay for that. But the ability to do so extremely easily, and remember back, you don't need any full-time staff to manage your clusters for you, the magic happens. And what's come available recently, but it's not quite globally available at the moment, you have to sort of opt in right now, is this multi-master. So you can have multiple locations in the world where you're writing data to, and that data gets replicated to all your other read replicas and your write masters everywhere across the world that you've got defined, and that just happens magically. That stuff's really powerful. It's really easy to do from a consumer perspective, and again, all that magic is taken care of in the background for you. It has these 5 consistency models. By default, it's session, and you can choose which one you want. It all has some performance and cost impact. Eventual consistency is a fairly obvious one. You're right. Eventually, the other read replicas become consistent. Going all the way to strong, you write, and then everywhere becomes consistent, but you've got to sort of wait for those to become consistent based on this quorum. And again, that usually takes a bit more effort, so you get charged a bit more. By default, it defaults to session, which means in your session, your data becomes consistent. So you make a write, and then you can read that data straight away within the scope of that session. If you break that session, you throw the client away, for example. There's no guarantees around that. The other two, consistent prefix and bounded staleness, sort of lean towards strong and eventual respectively, but there's a defined lag time that you can define. And again, it's kind of an in-between between strong, session, eventual, which are the more prominent ones. It's actually one of the few databases that offers those degrees of consistency that you can select from. And additionally, actually, you can change it as you go for the most part. So you can choose eventual, and then later on think, no, I'll go session, or I'll go bounded staleness, or whatever. The other really cool thing about it is the ability to support multiple APIs. It has a SQL API, and when I say SQL, it's a SQL-like API. It's not actually SQL or T-SQL, it just looks like it. It's got Gremlin for graph DBs, Table, Cassandra, MongoDB, EF Core. There's a few others that are coming as well, but it has a really flexible way to plop APIs on top of it. Once you choose an API, you can't go to a different API. So if you're writing Mongo, for example, that I think stores in BSON format, you can't sort of switch over to SQL and Graph. There is a bit of an exception in that if you choose GraphDB, you can actually use a SQL client against it because the similarity of the data is really close, but that's the only exception currently. It's basically wire-level API support, so when it goes under the covers in SQL, things get changed around a little bit. They are internally translated to something called an atom record sequence, which is unfortunately abbreviated to ARS. An atom being a primitive, which is a single string, number, and boolean. Record being sort of like a struct, and a sequence being an array of atoms or records. Just a bit more detail around that. So again, you've got your APIs coming in. Again, they're just wire protocols. It has these extensible module system, which in effect takes in that wire-level API request, efficiently translates that into this atom record sequence, but it's only an internal type system. They get materialized as a certain type of tree, but it's specific to the API itself, and then persisted, and then that gets reversed on the way up. So the actual persistence is a little bit different for each API, again, barring the GraphDB and SQL. So that's why you sort of can't chop and change at the moment. A little bit of a demo. Okay. So what I've got here, I've got two databases. We're going to jump into, well, not the graph one first. We'll jump into SQL. So I'm in the Azure portal at the moment. I've got, can you guys see that okay? Yeah? All the way at the back? Yeah? All right, good stuff. Excellent. So I've got two collections here. My CosmosDB account is currently Glove Demo SQL. I've got two collections, a small and a large. One is provisioned with 400 request units per second, and this one is 10,000. So what I'm going to do first, though, is I'm going to do a manual failover between regions, simply because it takes a bit of time, and then I'm going to go into a little bit of the other operations while that's happening. So what I'll actually do, not into there. At the moment, I've got my, I'll zoom in. I've got my CosmosDB locations in Australia East, and I've also got it replicated here in Australia Southeast. And what I'll do, just quickly, I'll jump into this little client that I'm going to run, and don't worry too much about what it's doing at the moment, apart from it's doing a select. Font, sorry? Font size, too small? All right, hang on a second. How's that? Better? Yeah? All right, cool. So all it's doing is running a query, doing a select query there. It's going to loop through some results, and it's actually just going to do a spinner to say that it's still working. It's doing a while true, so it's just a forever query. I'm not going to worry too much about the details at the moment, apart from the fact that it is running a query. I'm going to start that running, and it's zipping through. And there's no try-catch around this. If it falls over, it's just going to crash and burn. So I'm going to go here, and I'm going to say, all right, I want to do a manual failover. And my current write region is Australia Southeast. My read region is Australia East. So I'm going to say, I'm going to select that. I understand and agree to trigger a failover on my current write region. So away we go. Cool. So it's now doing a failover. If something bad happens while this is doing a query, this guy's going to show a whole bunch of blurb when it throws an exception. If everything's going well, we won't see anything. Now, let's close that down. So we go back into there. If I have a look at the Data Explorer here, you can see my small and large collection. Go into Documents. Yeah, it's going to be a bit weird. Select the document there. I'm going to zoom in a bit. Get out of the way. Oh, man. Sorry, bear with me one sec. Right. God, it's annoying. Oh, you can see I've got a... Oh, bloody hell. Why can't I move it? There we go. All right, so we've got a standard JSON document there. It's got an ID, an app ID. It's got a partition key here. We'll go into more detail about the semantics of that later. It's just a GUID right now. I've got an array of owned items. There's an address, which is a structure inside of it. Standard JSON document, nothing too special there. So I'm just going to show you some of the queries here that you can do. So right now, I'm just going to do a select star from C, obviously using the SQL API. Comes back with some JSON stuff. I could say where C app ID equals 13, 13, execute query, brings me back 13. What I'm also going to do here, if we go down, you see I've got these owned items, which is an array of, I don't know, was it 3 or 4 items? I can do a join, say join ONC owned items. I'll go up here and I'll say C app ID. What's the fields that I've got? Item description, category, seems easy enough. And show O category. Execute query. Oh, right. Ah, sorry. Okay, so I've actually done a join inside the document. So it's returning actually the same app ID, so it's 13, 13, 13, but I'm getting a different category based on what the internal array within that single record was. So I'm doing a join, sort of, but it's not really across records, it's just within that same record, if that makes sense. So it's SQL-like, it's not quite SQL. Additionally, if we have a look here at query stats, on that particular statement, you can see that that took 3.47 request units per second. So you can play around with a very small collection, for example, and get a feel for the cost of your queries that way. Just checking on my query, it's still going in the background, that's pretty cool. My manual failover has happened. Okay, so nothing really exciting has happened, which is kind of a good thing. In that for a failover, it wants to be pretty boring, right? You don't want any burning houses and screaming children. It just wants to sort of happen in the background. And now if I look at my replicate data globally, you can see my write region is now Australia East, and my read region is Australia Southeast. But I'm going to have to make that smaller and zoom in. So what about if I want to add a region? So I want to replicate to, I don't know, Canada Central. Yeah, it'll go there. Oh, I might want to replicate to, where's else can I go to? What the hell, Japan East? Yeah, bugger it, I'll do one more too. We'll go off to France Central. Okay. Sounds good. You can see, well, maybe you can't, you can see it's starting to light up these areas here on the map for me. I hit save, and now that's going to go and create a whole bunch of read replicas all around the world for me. I think that stuff's pretty awesome. And that'll take a little bit of time to do, but if we go back to that, you know, manually maintaining your own clusters, if you had to actually, if you were asked to try and set this up within your company without doing this, it'd be pretty damn hard. But this stuff is really powerful. Okay, going away from there. What I have to show you as well. Going down here to metrics. So you can see here it's showing me, generally I've got my nice little circle in Australia, which is where my main regions were. It's starting to replicate over here. That's all good, but that's not particularly exciting. I'm going to go to the throughput tab, and I'm going to select my Glav Demo SQL and my collection, which is a large collection. And quickly here you can see that my collection, large collection, has 5 partition key ranges. Provision throughput is evenly distributed across these partitions, which is 2,000 RUs per second. So while I have a collective request unit per second of 10,000, per partition, I've got 5 of them, I've got a limit of 2,000. So if my partition key is rubbish, and it all goes to one partition, even though I've got 10,000 RUs per second, I've really got a cap limit of 2,000, because it's based on a partition. Does that make sense? Let's click on 24 hours here. So this morning I provisioned some data, and I'd go back to, it's expensive to provision Cosmos at a high rate, so I've been building and tearing down my collections. I did that this morning. You can see there's been some activity. It was roughly around 20 past 8. And during that time, I've actually exceeded the throughput on one of my partitions. Well, actually, it's already brought it up for me, which is nice and handy. Here on the maximum consumed RUs per second, you can see it's listing out my partitions for me. Partition 3, not too bad. Partition 4, it's all good, still under the limit. These guys are just sort of getting pretty close to the limit. However, that guy's exceeded the limit. Let me just zoom in there. So that's gone above the 2K limit. So I would have had requests refused at that point. And the reason is because that partition key I deliberately put in as a static partition key of 1, 2, 3, 4, 5. So any time that records, and I've got about 20,000 records in there, any time that records were read or written using that partition key, it's all going to the same partition. And if I did it too much, which I did purposely, it's exceeded the the request units per second for that partition. So it's an important concept. If we go back to the whole partitioning is key is Cosmos, if you don't think about your partitioning and partition keys, you can pay for a lot more throughput, or what you think you're getting throughput, and it's actually not working very well for you. But I'll also go in just very quickly. If I go to my graph database, go to the small collection there, I'll execute the gremlin query, and I'm no GraphDB expert, mind you, so I'm not very good at queries. But I'll zoom in there, you can see it's displaying this graph for me. If I click on here, you can see the data change on the right over here. Click on Mary, bit of a different funky looking graph, that kind of thing. If I come up the top here, I can actually say I want to do a SQL query as well. Select star from C, execute that, and I'm getting back some regular JSON. That's just to highlight the fact that you can actually use SQL or the gremlin syntax with a GraphDB. Oh, my query is still running in the background, which is a great thing. Okay. So, local dev experience. I've mentioned about cost previously. You can provision up a 400 RU per second collection for Cosmos, which is relatively cheap. Oh, actually, sorry, let me bounce back very quickly. Sorry for being so bouncy. It is Friday. If I go into scale, I'm in the scale and settings here. I can change my throughput at any time. As I mentioned before, 400 request units per second cost me 77 cents daily. My largest collection that I have is 10,000, which is actually costing me $20 per day. I can go up to add another zero, and that's $192 today, and it's saying you're about to request an increase in throughput beyond the pre-allocated capacity, and you can keep going up, and you know the cost goes up. So you can get a good idea of how much you want, but you generally don't want to just provision something high and say, see how it goes. You want to take a sort of start off small and get larger. But 400 is the minimum. It's pretty cheap. Like I said, only 77 cents per day, but it's still a cost. So to get around that, there is a local emulator that you can install. There's a Docker version of it. You can just do a local install. It only operates off a single partition though, and supports SQL and MongoDB APIs. It doesn't have any consistency level simulation or anything, but it's enough to create collections, do SQL queries on there, and start testing out your application locally, potentially even do some integration tests against. But it works really, really well, and it costs you nothing. So that's kind of the base level where we're at. We talked about partitioning and APIs and consistency levels. You can do SQL queries. I'm not going to go into too much detail about all of that because that stuff's pretty easy to find out for yourselves. We are going to talk about some of the, let's say, interesting things that I came across as we were developing, which I will share with you and hopefully save you some pain, money, and or both. So I don't know if you remember when I went into the Azure portal there, we had a look at some of the records. I was selecting star where C app ID equals 123, and it all worked fine. CosmosDB expects an ID field in there, so when you create a new document, you always get an ID. You get a few other fields as well, which we'll look at soon. But coming from a SQL background, you might think, all right, I'll select star from ID, or where ID equals 123. And she's good, that should be like a primary key almost. It's very, very efficient. The complete opposite is actually true. While it will work, selecting via ID costs significantly more, and I'll show you that in a second. In fact, I'll show you it right now, and there's a rather bizarre reason for that. So let's go to my SQL. I'll go to my large collection. I will make it a bit bigger. Just go new SQL. Actually, I'll click on this document first. And you can see in my documents, I've deliberately got app ID and ID. I've created app ID as part of my data creation. I've deliberately made app ID and ID exactly the same values for all my records. So I'll say new SQL query, select star from C, where C app ID equals 123, let's say. Execute that. We'll get some data back. The query stats. It says over here 3 request units per second. I'll change that to be ID, exactly the same value. Go to results, execute query. Get the record back. Everything seems to look great, except it's now 177 request units per second. And that'll get more and more the more data that I put in there. And like I said, I've only got about 10,000 at the moment. But it's an easy mistake to make. I'll talk about why in a second. They're coming from a SQL background. You think, I've got an ID, I'm going to select by it, set that up in my application, good to go. If you do that, you're going to be consuming large amounts of request units per second beyond what you'd initially thought. And the reason for that, it's actually by design. So they, when I say they, the CosmosDB team, we're back up, yep. Initially thought that the ID would not be unique across partitions. You'd have to combine it with the partition key. And so you get indexed, everything by default gets indexed in CosmosDB. The default index just says index everything except the ID field. They decided to exclude it for whatever reason. It's not really well known. But again, their reasoning is that the ID is not unique, so you get charged extra for it. That's how it just how it is currently in this index v1. There is an index v2 coming, but it's not available yet. You can ask Microsoft to opt into it, and it takes care of this particular problem. And you also get extras on top of it, like I think there's an int64 optimization specifically to optimize for dates, multiple group by clauses, and a whole bunch of other things. However, the practicality is that don't rely on the ID field. Select by something else, and it'll always be much more efficient than that stupid thing. It results in pretty much a full scan. The only, I think the only exception is if it is actually the partition key. I think they do some special semantics around that. But other than that, it just generally results in a full scan and a crap load of RUs, which you'll have to pay for. Portal metrics, these guys have changed a little bit over time. When I was using it, actually let me step back a little. When you're performing requests against it, like selecting star for data, that goes against the data partitions, which as you'd expect. And these guys can dynamically scale as required. When you're requesting or creating a collection programmatically, you're requesting the name of an index or the list of collections that you've got, it all gets stored and accessed from this master partition, which gets provisioned for you. There's only one of them. It isn't automatically scaled for you. And until recently, the master partition and the metrics around it weren't surfaced in the Azure portal. And the reason that's important, even though it is surfaced now, it's still not that obvious, is in a lot of the examples there, you'll see up the top, and a lot of the stuff that Microsoft provides, it says, all right, let's do this, create database if not exists, and then we'll create document collection if not exists, and then we'll create the actual document. So those two statements above will go and hit the master data partition, well, twice in this case, before doing one request against the data partitions, which are far more scalable. But effectively means you're hitting the master partition, the non-scalable part, twice as much as you're hitting your data partitions. And it will not blow up, but it'll start to get 429 and request rate throttle, those kinds of things, if you use these particular examples. What you typically want to do is only do that when your application starts. So create the database and the collection, and then only do data operations thereafter. It's just so prevalent in a lot of the documentation that's easy to do your, you know, as all coding geniuses do, is a copy paste into the code and run, and you're all good to go. And like I said, it didn't actually, what I should do is go back into the portal. This actually wasn't surfaced previously, so if you did use that kind of code, you would get 429s, but the metrics in the portal wouldn't show anything. So if I'm going up here, we have a look at the system tab over here. This is where it's now surfaced. Right now you don't have, there's no 429s, nothing's been refused. I've only had a few requests against the master data partition. It's all good, so they've obviously decided to surface that. However, again, that's not really documented very well, so unless you know to look in that system tab at the master partition, you might not realize that that's why you're getting throttled if you're using those particular code samples. And I just saw a notification that my add remove regions has worked, so I'm now replicated in multiple regions across the world. I think that's pretty cool. Back here. So that's the kind of the server-side portion of it. I'm going to concentrate a little bit on the client now because that's just as important. In particular, the document client, which is generally the more popular one. And it's quite important to get the most out of CosmosDB. I talked about parallelism before with, I don't know if you recall the spectacular animation, you probably... but the document client they use for Cosmos is quite heavy. I don't know if anybody has ever used WCF and the client that came with that, but it was quite heavy as well, in addition to having some weird advertised semantics around it, but it was quite heavy. You had to be very careful how you used it. It's the same with document client. And the recommendation is you only keep, you pretty much keep it as a singleton if possible, and don't recreate things all the time, don't recreate the client. It is thread safe, it's built to be thread safe, but it implements iDisposable. So if you were to drill down and have a look at it, you think, oh, it implements iDisposable, I should do a using statement each time I access it, and semantically you'd be correct, but you'd be getting really crap performance out of it. And one of the reasons is use this open async that you see there. So what that does, if I jump into some code briefly, let's go up here. In my particular instance here, I'm creating a document client and I'm calling open async before I do anything. What this does is it goes out and grabs an address routing table, which usually involves up to 8 requests. And if you consistently recreate your client and you haven't done this call before making a query, it'll go and do this in the background for you. So if you're continually recreating your client, it'll do open async and then the query, and then you're getting 8 to 9 requests potentially per one request, and so you'll see your performance suck badly, and it won't be apparent why. So make it as a singleton, call open async, and then start to do your document operations. And again, that one's actually not. There are documents out there that suggest this is what you do. It's not really obvious why, and it's not. I don't think it's communicated that well. There's a connection mode. There's 2 connection modes you can use, gateway and direct, and they offer different protocols. Again, I'll jump into a bit of code here. By default, if you don't do anything, well, that's hard to see, it defaults to gateway, and if you use gateway, the only protocol that it supports is HTTPS. It is actually the slowest way of doing things. But the reason it defaults to that is it's the most firewall friendly. So if you've got some port restrictions, that will usually work just fine because it'll just go through 443. However, if you can get away with it, use direct and TCP. It opens up a bit of a port range. If you're using an on-premises VM, for example, you might have some security restrictions that might be problematic. Typically, if you're using something like an app service in Azure, this works just fine and the performance increase is significant, just from those 2 options alone. I mentioned parallelizing your operations. So whether this be a virtual machine or it's an app service in Azure, if you're a virtual machine, the more cores you have, the better. And utilizing something like the task library to get as much parallel operations within that single machine will yield significant benefits. Similarly with an app service, you'll kind of want to scale out if you really want to take advantage of Cosmos. If you're doing a bulk operation via an app service, whether that be via web job or something, you'd be best to span that out to, let's say, the full 20 instances while that operation runs, and then perhaps shrink it down. If you're using just like, I think it's an S1, which is probably just a single core, and you're using the task library, you're not going to get too many benefits from it, and you're going to see that your client is constrained. It's not Cosmos that's not performing, it's actually the client that can't parallelize enough and feed enough data to Cosmos. So whichever way you can scale out And the more you can scale out, the better, and Cosmos will just chew that up, provided you've allocated the right request units per second, of course. And there's usually a bit of fine-tuning that comes with that based on your workloads, based on how much money you want to spend, and the use case. This was probably in retrospect fairly obvious, but this one caught us a little off guard. We were trying to prematurely optimize. So this request here, or this bit of code you can see, is just doing standard select, where the app ID might contain the number 1. And then you've got a loop there which is saying, if query has more results, then execute next, which is going to get them more results, and add range. And what we were doing previously is in the middle of that loop, and by default, sorry, the page length of Cosmos defaults around 100 documents or 100 records. So previously, in that loop there, we'd say, look, if you get 0 records, or if you get less than the current page amount, which is 100, we think we're at the end of our result set, and we're going to bugger off out of that loop, which was incorrect thinking, primarily because of the partitioning. And I'll highlight that right now. So what this guy's doing is nothing too spectacular. It's just doing a very simple query, again, where app ID contains 1. And then we're looping through it, saying how many records we got in that result set, and just looping through until has more results is false. So I'll run that. So what we see here, so we're looking at those results, you can see we get 100, 100, 100, and then suddenly there's 8. We've got 43 there. Oh, and if I zoom back out, oh, come on. Let me just run that one more time. And go back up. You can see there's a few deviations there, where in this case there was 11 records. Down here was 79, sorry. So going through that, you know, it's getting not the full page amount, and making the assumption that if it didn't get that, or even if it gets 0, sometimes you can actually get 0 records through that loop. Don't exit that loop. There's still more data to come as it cycles through the different partitions. So that, for us, while we were still in relational SQL land, operating like you do on a normal sort of paged result set. We shouldn't have done that. It was just really relying on the has more results. If that's true, even if you get nothing back, then keep iterating over. Yeah, the magic number. A little sad to see that it's still prevalent in there, but it is there. So one of the options that you can provide to your queries is this max parallelism. And I mentioned how important parallelizing your operations is. So if we jump quickly into code, you can see here, as I'm doing a query, I'm providing feed options, and I'm saying max degree of parallelism equals -1. Now if you leave out this, it defaults to 0, which is effectively the same as 1, I believe, and it just effectively goes through each partition in sequence. If I was to manually try and fix that, because as we saw before I had 5 partitions, if I set that to 5, that would actually still work pretty well. However, CosmosDB can scale out and down the number of partitions automatically for you. So you don't really want to have a config element that each time CosmosDB does that, and it doesn't tell you, that you have to change that manually. The easiest way is, of course, the magic number. This magic number, and this operates with a few properties within the CosmosDB client itself. Not just this one, but this one's one of the more important ones. -1 tells the SDK to manage it automatically for you. In this case, it'll say, hey, you've got 5 partitions, I'm going to set up 5 for you, and good to go. Which means if CosmosDB ever expands the number of partitions for you, the SDK will take care of it for you. This is listed in the documentation, a little bit too deep for my liking, but it is listed there. Okay. So just wrapping up briefly. I know I've banged on about it a little, but effective partitioning is going to help you a lot with Cosmos. Cosmos, again, can be expensive. You've got to be aware of how the partitions work, the partition keys, having an effective partition key. In my particular instance, I was just using a GUID, and there's a big spread. It's not particularly suited to the data, but it gives me a good spread across the partitions. If you wanted to make sure your queries were really efficient but still make use of partitioning, let's say you had some address data, you might use a postcode, for example, as a partition key, or at least a combination of that in your partition key, where selecting everything within a particular postcode might only hit that one particular partition, but it provides enough of a spread to get good distribution across your partitions. That could be something useful. Again, in our case, I've just put it as a GUID, good spread, I'm getting reasonable performance. And I'm making use of the partitioning of Cosmos in a good way. Parallelizing your operations, again, very, very important. You'll typically hit a point where your client, especially if there's only a few of them, is the bottleneck and it's not actually Cosmos. And you'll try ramping it up, but either the network is saturated or the client's just not, hasn't got enough threads available or cores available, whatever the case may be, and it's just not pushing enough through the pipe. And you'll think Cosmos is sucking, but it's actually not the case. If you're copy-pasting coding, beware of exceeding the master partition. Create your collections and databases at the start of your app. So if you're using dependency injection, create it as a singleton, as part of the initialization, create those collections, and then they're created for the duration of your application. And just be aware of all be diligent about client usage. Don't be frivolous with it. Treat it as a precious resource. Again, singleton, call open async. And there's a document I'll link to at the end here which has a whole range of performance considerations, but the ones I've provided to you here today are the ones that actually have made the most impact for me anyway. In terms of what I'd suggest you do, if you're not doing this already, install the emulator and just have a bit of a play with it for a start. It's free, you can't go wrong with it. Sort of going back to that bit of intellectual verbiage that we touched on before, CosmosDB can provide you all those magic items, but you need to work with it to make it do so, particularly around, again, partitioning and consideration around request units. It can do all that. The replication, for me, I think is absolutely fantastic, but you just got to work with it to get the most out of it. Have a bit of a play with it. If you're thinking of using it, make sure you do a spike or a proof of concept around it, because you'll have some preconceived notions about how you might want to use it. It might be for performing certain kinds of searches and queries, which may not work so well from a Cosmos perspective. Or it may just actually be, you may have to pump up the request units so far that it becomes cost prohibitive. So make sure you sort that out early. You don't want to go too hard, too fast and find out it's really not appropriate if you've bet the farm on it. Again, partition. Think about your keys and partitioning keys. If I had to just no-brain it at all, I'd always use a GUID and then get more refined from that. Automate your database collection and test data. For this particular demo, and I've done that for all clients that I've worked with Cosmos, is to make sure you remove any data or collections that aren't used. For this particular demo, because I've ramped it up to 10,000, I don't want to pay $20 a day. I'm pretty cheap. So I've got a piece of code, which I'll link to at the end of this as well, which will constructs up the database IDs, the collections, sets up the request units per second for me, and fills it all up with test data. So once I'm finished this demo, or this presentation, I'll run delete all and it'll just tear it all down for me. And that way I can actually get away with playing with 10,000 RUs per second collections quite easily. I'll spin it up for maybe an hour or two, or even a few hours, tear it down at the end, and I'm good to go. Yes, it still uses a few dollars, but it actually gives you a good feel to play with Cosmos in real life at high RUs per second with full partitioning semantics. So that way you're not just operating blind and not just relying on a 400 RU per second single partition or local emulation experience. I did have a interesting for one particular client where we were load testing CosmosDB, And the client was fairly generous in its Azure consumption. So we had, well actually not we, a particular developer decided, I'll give it a bit of a performance hit. I'm going to pump it up to 100,000 RUs per second, and I'm going to run some performance tests. And the developer did that. Sent me a report on findings, and it was okay, got to a certain amount. Thought nothing of it. A few months later, the manager comes to me and says, Paul, what's this $15,000 per month resource that we're using? I don't know. So I went and had a look, and sure enough, there's the 100,000 RUs per second collection sitting there doing nothing with no data in it, but just hanging around, earning some Azure credits. But suffice to say, we deleted that. But just tear it down when you finish it. It's actually really easy to recreate. And like any good testing scenario, ideally you want to be able to recreate and put any of your test data in there, spin it up, run it, tear it down again. More so in the case of Cosmos. There's some links there. The tips that I showed you and the client usage in particular, I've got a blog post there which I go through about 20, I think it's about 20, maybe 25 individual tests where I go through a whole bunch of client options to find out which ones were the most important and had the most impact. Because if you look there, the next link there is the performance tips, which gives you like a few pages of performance tips to use, but it's not immediately apparent which ones have the most benefit. And so it took me a little while to turn this one on, turn this one off, spin up the number of threads, try an app service, try a VM, blah, 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 and all the different feed options. And in that, it's fairly comprehensive, although it could be more comprehensive, but it gives you a good idea of which client options have the most benefit, and that's the things that I've reflected in this particular presentation. However, if you're interested in more detail, go to that link at the top and you'll see the full sort of diagnosis. CosmosDB University one is a really good resource for any Cosmos information. There is stack loads of information there, and it's way too much to go through in any short amount of time. But there's just stacks there. There's white papers about the theory behind it, which is quite complex. I pretended to read it and understand it, but you know. And the link at the bottom there is all the source code that I've used for this talk, including the way I've created the data and the test data and everything. So feel free to have at it. It would be remiss of me to not mention the fact that I had been speaking to the CosmosDB team who have helped me in this presentation, and they were extremely receptive, even though they're extremely busy. And they really want to get things right with Cosmos. So they're very open to suggestions. Now, whether they do it or not, who knows. But one of the Cosmos engineering team was kind enough to take time out of his day to regularly connect with me and provide me some information around some of the information that I've provided to you here today. So that's about all I have for you guys. There's probably about 7 minutes left for questions. If anybody has any questions. I think you were the first one.
Does Cosmos support transactions?
So the question is, does Cosmos support transactions? The answer is yes, but not through the document client. You've got to do it through stored procedures. So it's got to be through the JSON level stored procedures, and they do provide atomic behavior there, but that's the only way it does it currently. Sorry, you had a question?
Spreading your partition and using who to start with. And when would be a good time to cluster a bunch of documents together with the same partition?
So the answer, the question was talked about spreading the partitions using a GUID and a good partition key, but when would be a good time to cluster it? And it's a hard one to definitively answer, generically answer. But in the case of I gave the postcode example, where you might want to cluster things by location, and you could have a partition key as a postcode. But where you've got closely related items and the data is not too massive, if you've got a heap of data that's tightly clustered, you probably want to think of a composite partition key that will allow it to not spread too far, but still be partitioned, if that makes sense. It's a little bit of a tricky one to answer because it's so crucial to how it works. You'd have to really spend some good time analysing that and doing spikes and proof of concepts as to how that was spread, using the Azure portal metrics to determine how well it was spread. Does that answer your question? Yeah. Any other questions? Yes?
You showed OpenAC. I assume that's not the same thing that starts a session.
No, that's purely for filling up. Well, actually, no, sorry. It will. As far as I understand it, its primary use is just to get the address routing table. I don't think it creates the session, but it could do. I'm not 100% sure on that one. I'd have to go back to the team and ask. I will do on that one though. Any other questions? Yes, up the back.
So how would you really know when to break out of that as records if you don't have really no records?
Okay, so the question was, how do you know when to break out of that while loop for have more records? And you touched on the answer there. So it's when this guy here is false. It's as simple as that. Yeah, so when it has more results as false, it just exits out. Yeah. Yes?
What do you think, which scenario is actually more suitable for CosmosDB versus like traditional SQL?
So the question was, which scenarios are more suitable for CosmosDB versus the traditional SQL? First and foremost will be reporting. I'd use SQL for reporting almost always. In terms of other scenarios, bulk ingestion is good, so really fast ingestion of data. It also has a change feed mechanism, so if you want to listen for changes in data and you want to trigger something else, it's really good for that as well and quite efficient. As to other scenarios, I'd hasten as to provide a generic answer, and as a consultant I would be doing myself a big disservice. But I'd have to examine the scenario itself, and it's really about looking at that data. If you were expecting it to operate in a SQL-like way and you want to do relational constraints, then clearly that's not the way to go. You'd have to implement that at the application level. If that was too much of a cost, then I wouldn't recommend it either. But that's a general sort of NoSQL answer too.
Basically, it's not like even in the long term, not a replacement for traditional relational databases, right?
No, not at all, not at all. But if you're doing things like doing Mongo development and you want to take advantage of some of the replication and consistency levels within Cosmos, it's a really good option because you can retain your Mongo knowledge and usage thereof, but you can get all this wonderful replication and high availability that comes with it, and throughput as well. Yeah. Yes.
Then when you're selecting among the 5 different consistency models,
Mm-hmm.
what's the granularity at which you can make that selection? And if it's at the collection level, can you join across collections that have 2 different consistency variables?
So the question was, what is the granularity of the consistency levels, and can you join across collections? I'm not sure how to answer the granularity of the consistency levels. I mean, for me, the eventual, session, and strong are probably the most obvious ones. Difference between eventual and strong is fairly obvious. The session, again, is a little bit different because it tries to provide a localized version of strong, but it's just not geographically redundant. The other two, you can tune the window of latency between the two. Because in between eventual and session, you can tune the amount of eventual prefix I think it's like the amount of time in terms of seconds that the other read replicas become eventually consistent. And similarly with the strong, I think it's bounded staleness, how much time before all the quorum becomes consistent. So you can get down to a per second time. I don't know of any restrictions around that, or the timing, the window timing, but it's generally in between 1 to 10 seconds you can kind of define, and you can move a slider along to determine that. In terms of joining across collections, that you don't get that. Yeah. Any other questions? Okay, well, I'll be hanging around for a little bit. Thank you very much for coming. I realise it's one of the last sessions. You're probably pretty drained, but I really do appreciate you turning up. Thank you very much.